we're doing derivative. Oops. Oops. Trig functions. And we're going to do chain rule today. And chain rule is one of the hardest / mischievous rules that we have to take into account whenever we're taking any derivative, even the power rule derivative. So I'm going to start talking about that today. So let's talk about first the derivative of trig functions. So here's a list of trig functions that we need to know. Derivative of sine is cosine. The derivative of cosine is negative sine. Please remember the negative because it's going to screw you over hard. The derivative of tangent is a weird one. It's secant squared x. Okay, it's weird, but it's cool. Okay, so whenever you do tangent, always secant squared. Let's do the reciprocal identities. The derivative of cosecant, that is negative cosecant cotangent. The derivative of secant is secant tangent. And the derivative of cotangent is negative cosecant squared x. So let's quickly review the easy ones. The derivative of sine, easy, cosine. Derivative of cosine, not the same as sine. It's going to be negative sine. And it's important because we'll look at this graphically, and it's actually a negative version of it. The derivative of tangent is secant squared. That's straight memorization. I don't like cosecant, so let's go and do secant. And this is how I do secant. I say the derivative of secant sounds like a sneeze, okay? The derivative of secant is secant tangent. Oh, that didn't make sense. Oh, all right, I totally killed it. Okay, so the derivative of secant is secant tangent. Just say it really quick, okay? That's the only way I memorize it. The derivative of secant is, just say quickly, secant tangent. It sounds like a sneeze, okay? For some reason, that sticks with me. And the derivative of cosecant is cosecant, right? It's the same thing, cosine, cosecant. Cotangent. So the cos, in a sense, stick together there. But there's a negative sign for that one. Okay? So here's another way to memorize. Which one gets the negative? Co sucks. So whenever you have a co, it's going to be bad. Whenever you have a co, it's going to be bad. Whenever there's co, it's going to be bad. So all the co's have a negative sign. Here the negative. Cosecant, negative. Derivative of cotangent, negative. Okay, so a couple of tricks for you to help you guys memorize this. First, easy one. Derivative of sine is cosine. Why can't everything be this easy? Then every other one is not. There's a trick to it. Cosine is negative sine. The derivative of tangent is secant squared. But cool, part about cotangent, it's just not secant, it's cosecant. It's the other one, right? And then the co makes that negative. For secant, secant, excuse me. Sorry, I say it so fast that it actually stalls out. But secant tangent. And the derivative of cosecant is cosecant cotangent. you will need to memorize all this stuff. Okay, so the dumb questions are, for instance, what is the derivative of x squared plus sine x? And since it's a plus, that means we can treat these problems separately. That means we'll take a derivative of the front and then we'll take a derivative of the back separately. So why don't you guys do that real quick? Take you literally like 5 seconds. And write that down before I write down my answer. X squared becomes 2x plus cosine x. That's it. The derivative of tangent x plus 4x squared plus 3x plus, that's a win for us. Oops. Right. Is equal to secant squared plus 8x plus 3. Let's throw a constant in front of that. The derivative of pi sine of x. Pi is a constant. That's just a number. So we use the rule constant multiple. Means we're multiplying by constant. That means we leave it alone. And what's the derivative of sine of x? Okay, constant multiple rule. And this becomes pi sine of x. You can definitely just jump to here, but this is what's going on in your brain.
What do you mean?
The constant just steps aside. Oh, sorry, you're right. I made a mistake at the end. I'm just copying. That's what happens when I copy someone else's homework. I'm not copying anyone's homework, I'm just saying. Okay, so this is great. Sine, cosine, tangent, all these trig identities, it's just straight memorization. Well, now, but what if I give you this? That's not my rule. That's not my rule. What the crap? So we have to go through this weird process. And what if I say this? What if I say u is equal to 2x? And I rewrite this as sine of u. Right? That looks like my rule. But it's the wrong variable. So this guy needs to change. What the world? What letter does dx have to be? This has to be du, doesn't it? Because it has to match up the variable inside and the variable I'm taking the derivative respect to. Okay, so this is our process to start talking about chain rule. My rule that I have memorized is only sine of x, sine of a variable. No one said to bring your little brother. So what are we gonna do with him? Stick him in a bag and call it you. Put a hat on. Okay? Put this bag over your face. So this is the process. This is like the algebraic process. I'm gonna change dx to a du so I can use my dumb rule again. So here's the long way about it, and I'll tell you guys what the short way is after we talk about how do we discover this. So how can I get u to become du? So what's the idea of a d? It's the derivative. So that's take the derivative of u there. So the derivative of u is equal to, what's the derivative of 2? That's a constant, and 2 dx. Okay. If you guys want me to write down one extra step, I'm taking the derivative of u equals to the derivative of 2x, which, like we showed just in a previous problem, the 2 comes out like a constant, and the derivative of x becomes dx. Okay. Now, I want to swap out my dx for du, so we're going to solve for dx here. Okay? So rewriting this now, d over dx is now du over 2 sine of u. Look, it literally is an algebra substitution. It's an algebra substitution. Let me erase this so you guys can all see it plain as day. The dx gets substituted with a du over 2 in algebra substitution. Rewriting this nicely, this is equal to 2 d over du sine of u. D over du sine of u. Now we look at this part here. What is the derivative of u with respect to u? This is just cosine, oops, of u. Now we have to plug back u again. We said u was 2x. And that is chain rule. Sounds like a lot of work, right? So let's repeat the concept. Concept is super important, okay? The important part about chain rule is that I can't take the derivative of something that isn't a rule. Sine of u, sine of x is a rule. Sine of 2x is not a rule. So what I do is I blur the lines. In algebra, you can do substitution whenever you want. So we substituted that. That's the idea. Yeah. I go ahead and change dx to a accomplice du, but du carries some ramifications. And then so when we brought the du on board, we had to change that to du over 2. So algebra happens, and we end up with our straight definition, derivative of sine u over du. It's just cosine u. Okay, nobody wants to do that. But that is the proof behind why this works. Now, I want to show you something kind of cool. If I did this sine problem, and I did this, and I said 3x, it would be 3 sine of 3x. Oh, sorry, I did keep doing it wrong. Sorry. 3 sine 3x, cosine 3x. If I took a derivative of sine 3x squared, it would be 6x cosine of 3x squared. Okay, so if I give you this one, cosine of x, the derivative of sine cosine x will be negative sine of x cosine of x. Anyone see a pattern? Let me give you one more, just one more. This is super obvious, okay? Sine of x, not x, sorry, of x squared plus 3x plus 2 is equal to 2x plus 3 cosine of x squared plus 3x plus 2. These are all chain rule examples. So if you take a look at that couple of examples, sorry I didn't record this part, but the derivative of the outside first, followed by the derivative of the inside. Derivative of the outside, leave the inside alone, followed by the derivative of the inside. Derivative of the outside, leave the inside alone, followed by the derivative of the inside. So the chain rule is all about, in essence, dealing with shells, like the Russian doll shell. You can't get to the next shell till you deal with the outside shell. So let's do a problem that looks a little different now. D over dx of sine squared x. Now, this is why I mentioned right at the first day of class that when you work on calculus, we're going to use everything we've learned since Algebra 1. Everything we've learned since Algebra 1. And you might say, what the hell? What am I supposed to do with that? I know the derivative of sine, but I don't know the derivative of sine squared. You're right, you don't. Let's rewrite this. This is the derivative from Algebra 1. And pre-calc, you can write this as, would you guys be okay that sine squared is really sine times sine? Yeah. Okay. Now, the outside shell is this guy. And that's power rule. So we just use power rule. Power rule is 2 sine of x to the 1 power. That's power rule. Leave the inside alone. Followed by, what's the derivative of the inside? Cosine of x. This is 2 sine x cosine x. Okay? To prove that this is true, I'm going to do what I don't want to do. I'm going to take the derivative of sine x times sine x using product rule. Isn't sine squared really sine times sine? Okay, let's do product rule. Derivative dx is going to be equal to derivative of the front, leave the back alone, plus derivative of the back, leave the front alone, all over, oh, there's no bottom, all over. And since you have sine cosine, oops, darn it. Don't we have 2 sine x cosine x? Oh my gosh, Mr. Ko. Ooh. Don't make me try to do this using limits. But the cool thing is that no matter how I write this, as long as in an equivalent way, the derivatives work. Okay, let me pause. Okay, yes, you can do that with tangent squared too. Real quick, derivative dx, tan squared x. This can be written as derivative dx, tan x squared. So doing our chain rule, derivative the outside first, which is a power rule. That's power rule. That's going to be 2 tangent of x to the 1 power. Don't write that. Times the derivative of tangent inside is secant squared. So remember, peel off those onion layers one by one. Okay, let's do one more. Derivative dx of, let's do 1 over sine of x now. Okay, let's see what happens here. You can rewrite this as sine of x negative 1. Huh? Yeah, see? If I take the derivative of this guy, it's negative sine of x to the negative 2 power, because we're minusing 1, right? And then derivative of sine is cosine of x. Okay? Double check it. We took derivative of the outside. That's where the negative and negative 2 came out. Derivative of the inside sine is cosine. All right, that looks pretty good to me. All right, let's rewrite this as negative cosine of x over sine squared x. Okay, but actually, that's not what I want. I'm gonna write this a little differently. This is really negative cosine of x over sine x times 1 over, 1 over sine of x, isn't it? Are you guys okay for me splitting that fraction? Cosine over sine, that's really cotangent of x. 1 over sine is really cosecant of x. And we can rewrite this as, oops, I went the wrong order. Cosecant, cotangent of x. Okay, make sure you're with me. Everyone okay with the one
Wait, Mr. Cole,
calculus step? Yes.
So why do you multiply it by 1 over sine of x after
Okay, I wanted to split this up. I wanted to split into two separate fractions.
Mhm.
Because we know cosine over sine, that's going to be cotangent. And 1 over sine, we can rewrite that as cosecant.
Right.
Okay? You might be saying, why am I doing this and all? Because if you remember your reciprocal identity, isn't 1 over sine cosecant? And the derivative of cosecant is negative cosecant cotangent. Proof. Okay, today's a short day, so I think we're going to stop here.